one. Okay, James Fader, it selected you to start us out.
Okay.
Okay. Maybe talk about the beginning of the lab.
Well, what is it?
Excuse me. Hold on. This is now the time that we've had our partner conversations. Now we're going to be sharing out, and so let's respect one another. Listen to whoever's got the floor. Right now, that's James.
Okay, so at the very beginning, the spring was compressed, wherever, and then there was like a whole bunch of energy within the compressed spring, which would be potential energy.
Okay, that's potential energy?
Yeah, potential energy.
Okay. What type?
I forget what it's called.
Elastic potential? Okay.
Yeah, it is. And then when the card is launched, that elastic potential energy is converted to kinetic energy of the card's motion. That's also simultaneously being converted into gravitational potential energy as it moves off.
Okay, so let's stop just at the first part. So you said right after it's released, this potential energy becomes kinetic. How did that mechanism take place? How do you change your kinetic energy?
Well, there was work being done.
Okay,
Yeah.
That's true, right? If there's a net amount of work, we're going to change kinetic energy. Let's think about what forces are doing work on it.
There's a force that the spring applied to the card.
Okay. There was a backing plate, right?
The spring did not apply. The backing plate.
Well, I wasn't actually here. I was taking a test.
Oh, that's true.
I don't know exactly what it was, but
okay. Well, that's a good question. And no, these two guys were discussing what was actually doing the work. What was pushing on what to give it kinetic energy?
The spring, like the fact that it was stuck in that gave it potential, like Jamie said, basically.
So the piston comes out. The piston was doing the work.
Oh, piston.
Oh, that's nice. That's nice word. The fact that it hit the
Yeah, the cart did put a force on the backing plate.
The
Backing plate didn't move. And remember, if you're the one putting forces on something else, you're potentially changing its energy, potentially. The only forces that are going to change your energy are forces applied to you. So what forces were applied to the object to give it kinetic energy? Well, you were right the first time, actually, Isaac, because you said the backing plate was pushing this. Okay. Yes, this was pushing on the backing plate, right? But the backing plate was pushing back with an equal and opposite force, doing work on it. Yeah.
Since where you can say that the piston and the backing plate are in constant contact, we call them like part of the same working. Like they are now like together. They're both not moving. This piston doesn't move when the spring is releasing, so it's the piston and the backing plate both not moving and the spring pushing the car.
Well, I don't know about that. I'd say that the external push of the backing plate on it would be the cause, because otherwise we're dealing with an internal force which shouldn't change its motion. Okay. All right, anyway, so yeah, we've got work being done by the backing plate on the cart, or on the piston of the cart, changing the energy to kinetic energy. Okay, pretty good. Let's move on from there. Markel. So now it's on its way up. What kind of energy transformations do you see as it's moving up to its highest point?
I see that the piston is like out now. So like as it moves up, like the energy is like I don't want to say going away because energy can't be destroyed.
That's true. Good point.
It's like the output is like not giving much more energy to keep it going up.
Okay. What's happening to the kinetic energy as it's going up the ramp? I guess
Changing.
So is it going up or down?
It's going like down.
down. Why? How do you know it's going down?
Because like the
Excuse us. Come on.
because of the angle of the ramp, like
What do you physically see happening to know that it's losing kinetic
slowing
energy?
down.
Slowing down. Yeah. So we've got a decrease in kinetic energy on the way up. But as Markel explained, you can't create or destroy energy. So where is it going? Yeah, you can.
As it's going up, it's turning into potential gravitational energy.
How do you know that it's gaining gravitational potential energy?
Because it's as it gets higher, it's like getting farther from the ground, so it's gravity force will increase.
Yeah. As delta Y grows, right? You're going to have an increase in gravitational potential energy. Okay. Cool. Now it gets to its highest point. Okay. And let's see who's going to talk to us about that one. This seems random again. I don't know how. It's pulling people we don't usually hear from. Helena's not here. And then it's going to go to Kathleen next, right? No, it's Mindy.
You shouldn't have said anything.
Okay. So we've discussed so far. The story goes all elastic potential at the beginning. On the way up, it's going. When the spring's released, now it has kinetic energy. On the way up, it loses that kinetic energy and it turns into gravitational potential energy. At the highest point, can you describe the energy transformations or the types of energy it has?
When you just have the gravitational energy.
Yeah.
When you just have the gravitational energy,
You say it just is going to have gravitational potential energy. Okay. I agree because it does have a vertical displacement. There's got to be gravitational potential energy. And it's at its maximum height, so this has got to be the maximum. What about the kinetic energy?
I say that there's no kinetic energy because it's at the highest point, so it slows down.
Yeah, what does it physically do right at that highest point?
It stops.
It stops.
Which means that no work is being done.
So there's no network. Well, actually, the kinetic energy is changing, so there actually is still work being done.
Oh.
So let's talk about that, right? So that was the one thing. We pretty much covered all these energy transformations. On the way back down, the opposite thing happens here. You lose gravitational potential, you gain kinetic. But I think we were having trouble maybe identifying where work was being done
Just a little bit.
as we're going up here. What's doing work on the card? Anybody? Okay, I've got two. Asher, we haven't heard from you today.
So there's the force of gravity that you, on the way back down, the force of gravity is moving it.
Okay. Is gravity affecting its motion on the way up?
Yeah,
Yeah.
but
Okay.
you can especially see it on the way down, so that's why I brought that up.
Okay. Right.
Oh yeah, and don't forget friction.
What other? Okay, so there was some friction, and we're going to say it was insignificant because those axles were really good. Those things would go really far. Well, what else was there? Only one other force, guys.
Tension? Oh, normal force.
Okay. Now look, it's being displaced in this direction. So, how much work is the normal force doing on it?
0.
How do you know?
It's not getting pushed through. It's not lifting off.
Yeah, there's no component of the this is the displacement, by the way. This is not a force, so I should actually move it somewhere so don't get confused as to it being a separate force. Okay, we're displacing up the ramp this way. Remember that there's got to be a portion of your force that is parallel to your displacement in order for that force to do work. Or if you just want to look at the angle would be 90 degrees. No force being done by the normal force. But what about gravity?
Gravity is.
Yeah, it is working on it. On the way up, it's doing negative work. On the way down, it's doing positive work. Right? Because there's some component of the gravity that is down the ramp and parallel to the ramp. And Isaiah mentioned friction. Friction's actually doing work the whole time too.
But like
Small
insignificant
amount.
though.
Small amount, yeah. What type of work is friction doing the whole time?
Trying to stop it.
It's negative. It's always in the opposite of the displacement. Okay, that's negative work. Okay, it's pretty good, guys.
Wait, can you explain how it's doing negative?
Absolutely. So on the way up, right, friction is acting in this direction. And so since it's going in the opposite direction of the motion, it's taking energy away.
So the opposite is taking the motion away?
Taking energy away. And if you want to think about it in terms of the equation, if the equation helps, the angle between the friction and the displacement is 180 degrees. And that's a negative 1 for your cosine of 180 degrees. So that's negative work as well. And then on the way down, your displacement is down the ramp, but your friction is up the ramp. So it's still negative because they're pointing in opposite directions. Gravity, though, gravity is on the way up, it's pointing in the opposite direction. On the way down, it's pointing in the same direction, or there's a component of it. So you've got that stuff going on. Didn't these things, when they came back, they bounced a few times before they finally came to a rest?
Yeah, because the spring keep trying to bounce it off of it.
Mm-hmm. Well, wait a minute. Markel told us that energy can't be created or destroyed. But how much energy do we end up with? At the very end, if you let it keep bouncing.
I know we just stopped it.
You end up with no potential and no kinetic.
Oh.
Wait a minute. Where did the energy go? I've been lied to all my life.
When did you the spring?
Well, the spring is not compressed anymore.
It just went out into other forms that don't come back into the equation. The friction turns into heat, so it just
That's
goes
right.
back.
That's right. So there's another. I mean, there's multiple types of energy. Heat is a form of energy, and so every time you strike that plate, sometimes you move the plate. Actually, you didn't work on the plate, but you're losing energy there mainly due to heating up things. Smack yourself across the face if you don't believe me. Your face gets a little warm. That kinetic energy is warming up your face. All right. So we have another problem set to consider. Next week we're gonna